Everyone, I'll be doing a poster presentation called Cost-Effective Variant Calling with DRAGEN using Illumina Connected Analytics, which is abbreviated as ICA. So whole genome sequencing is a method for determining the entire DNA sequence of an organism. For Homo sapiens, the number of base pairs is about 3 to 3.2 billion. So that's quite a big number. Variant calling is a process in which variants of a genome are identified using the sequence data. So the pipelines and algorithms used in whole genome sequencing require a large amount of computing resources. And so Illumina has developed what we call the DRAGEN pipeline, or just DRAGEN. It's an abbreviation for Dynamic Read Analysis for Genomics. Now, the DRAGEN server consists of an FPGA. FPGA are field programmable gate arrays. These are logic devices that are programmable, and they've got integrated circuits that are configurable. And this makes the variant calling very fast. So DRAGEN is accessible on the cloud through the ICA platform. And this entire study is working entirely on the cloud. We're just looking at this particular solution. A DRAGEN server can be purchased, the physical one that can be run on-prem. So when you run DRAGEN in the cloud, you incur costs by compute and storage usage. And we measure this in something called iCredits, but an iCredit is simply equivalent to a US dollar. So our objective is to minimize the time that data stays in the cloud, and thereby reducing costs, at least at a large scale. So the method we use here is we take advantage and use Illumina's ICA v2 command line interface, and we've developed something that I'll call the optimization workflow. It's built with Nextflow, Bash, and the ICA v2 command line tool. We use this workflow on 2 datasets, both of them public, Simon's Foundation Data Project and the 1000 Genomes Project. Our workflow is run on an HPC, which is a high-performance computing cluster, and we use Slurm to schedule our jobs. The output is downloaded from the cloud and stored on a file system. Now, what our workflow tries to achieve or optimize is the time data spends in the cloud. We cannot do much about the compute because when you run the DRAGEN analysis, behind the scenes there's a DRAGEN server scheduled to run it. We have no control over that part, but we can control the time in the cloud. So what we do with this workflow is we upload data, and then we start running the DRAGEN pipeline. While the DRAGEN pipeline is running, we call it an analysis. While the analysis is ongoing, we keep polling and we check the status of the analysis. If the status is succeeded, once it is succeeded, we proceed to download the output folder, and then we go back and delete all the data relevant for that particular run. So we delete the input data and we delete the output folder. If the analysis fails or gets aborted, then we just end the workflow. And so we see by our table and the graph say that the relationship between the DRAGEN runtime, so how long the analysis took, and the number of iCredits spent is, as expected, it increases. So the longer the DRAGEN runtime, the greater the iCredits used. And the input size may also be a factor, but the input size will be a factor in that larger inputs would require more analysis, would require more processing, so the DRAGEN server would run longer. But how we can try to get an idea of how much we're saving, in terms of storage at least, is to look at the wall clock time and compare it to what would have happened if we had to run each analysis in sequence, in series. So let's consider a batch of 2. Let's just say 2 a couple. So you take a couple of samples and you start your optimization workflow on both of them, and you let them run concurrently or in parallel. And this is shorter amount of time than if you had to run one to completion and then run the next one to completion. And you'll see when you move to 3, a batch of 3, and eventually a batch of 4 samples, the saving becomes more and more significant. The reason why you don't see such a drastic difference between batch of 2 and 3 in this example is because they were taken from 2 different data sets. And the Simons Foundation data is much bigger than the 1000G. When we get more data, more samples to work with, we will be testing on more examples of batches, so a batch of 5, a batch of 10, a batch of 15, and so on. So this is an ongoing project. So in the discussion, we'll see that, as I said already, the longer DRAGEN runtime, the greater the cost. Nextflow allows us to run things in parallel, and this parallelism is what allows us to save on overall time, and this time savings translate into storage cost savings. The other good thing here, in conclusion, is that the workflow is reproducible. It's open source. We share the workflow on GitHub, and DRAGEN is got quite a few different pipelines. We're not bound to whole genome sequencing. We can do other stuff, exomes, transcriptomes. Our plan, as far as I know, as of now, is to look at joint genotyping in the future, where we'll do some pedigree-based joint analysis. And that's it from me. Thank you, and bye-bye.